Hello everybody, we're back with another chemistry problem, and this one's coming from a Luke Barber out in Eagle Point, Oregon. Okay, Luke's question for us today, I don't have it written down here, so you have to excuse me. It is, how much power can be given off by the combustion of 360 cubic centimeters of octane? It's a good question, and we're going to jump right into it. So the first step, as we can see here, is find out chemical formula for combustion of octane. Well, actually, it's going to be a chemical equation. And the equation looks like this. We have the formula for octane being C8H18, and there's a small L there in parentheses annotating that this is in its liquid state. And it mixes with oxygen gas, which comes as O2 there, and our byproducts of the combustion of this reaction is going to be carbon dioxide as a gas and H2O as a liquid, or water as we all know it. So that's not the end of the story here yet, because we have a problem, and the problem is that equation there is not balanced. So what we have to do is balance the equation so that all of the products on the right side match up with the reactants on the left side. And we're not going to get into exactly how to do that in this video, but the solution is going to look like, with whole numbers, whole integers, and no decimals, it's going to look like 2 C8H18, 25, and sorry for the poor penmanship there, it's going to be 25 O2 as a gas, 16 CO2 as a gas, and 18 H2O as a liquid. Don't mind this table of information. We're going to get to that here in just a moment, but there you have it. There's the balanced equation for the combustion of octane gas. Step 2 is going to be using the thermodynamic data, which is this table here, to calculate the enthalpy of reaction for the combustion of 360 cubic centimeters of octane. So that's where this information comes into play, because it turns out the equation for calculating the enthalpy of a reaction, or how much heat is either giving off of the reaction or being added to the system of the reaction, is going to look like this. So the enthalpy of the reaction is equal to the sum of the enthalpies of formation for the products minus the sum of the enthalpy of formation for the reactants. And that's this sigma notation here. That means the sum of. Also, something to note with these little degree things here on the enthalpies of formation and on the reaction, they should be here as well. That means that all of this is going to be under STP, or standard temperatures and pressure, which is going to be 298 Kelvin for temperature and 1 atm, or 1 atmosphere of pressure. Okay, so moving on. We know that it's going to be the sum of the enthalpies of formation for the products minus the sum of the enthalpies of formation of the reactants. And this is in regards to this equation. And a little orientation here, everything on the right side of the equation is going to be the products, because they're what are produced out of the reactants. Okay, and we see that also annotated here with reactants and products. And we have this information that tells us the standard enthalpy of formation for C8H18 as a liquid is negative 249.95 kilojoules. And then we have 0 for O2. And this is because one of the laws of thermodynamics, or one of the principles, is that elements in their standard state, which is oxygen, or standard state being how we find them, and this is usually how we find oxygen in the world around us, is going to be 0 at STP. And then we also have the enthalpies of formation for water and for H2O and for CO2. And those are right here, negative 285.83 kilojoules for H2O and negative 393.51 kilojoules for CO2. Okay, so now using that information, we'll plug it into this equation, and we have products minus reactants. And notice here, in the side of this sum of the products, I have not only its enthalpy of formation, but multiplied by these coefficients here. Can you think of what these coefficients are referring to? Well, they're referring to the number of moles of those materials we have in our balanced chemical equation. Remember, and these coefficients here can identify moles as well. So we could say 2 moles of C8H18 and 25 moles of O2 reacts to give us 16 moles of carbon dioxide and 18 moles of liquid water. And what a mole is basically taking numbers that are very, very small usually from the periodic table and elements, because we're talking down to just atoms here, 8 carbon atoms and 18 hydrogen atoms. It's taking those very tiny numbers and bringing them to more tangible and workable numbers. So when we say 1 mole of something is 6.022 times 10 to the 23rd of that something. So if we said we had, for example, 1 mole of cars, that's going to be 1 car times 6.00 or 6.0 times 10 to the 23rd power. So this number here with 23 zeros going this way, which is a really large number. So that's why, and so you can imagine how small these are down to the atom size. So that's why we use moles. And it allows us to make calculations like these much simpler. So that's what those coefficients are. It's telling us how much of each of these molecules there are in the reactions. So we have 16 moles of our, what is this one? CO2, it looks like. 16 moles of CO2 plus 18 moles of H2O, because we have products. And then we're going to minus the reactants, so it's going to be 2 times the octane, 2 moles of octane, plus 25 moles of oxygen, which we know from our thermodynamic data is 0. And after you do all the correct calculations, you're going to get this number, and it is negative 10,941.2 kilojoules of heat. And that's pretty big. And another way of writing that would just be negative 10.941 megajoules. I won't say heat, I'll say of energy. And we have an interesting value here. We have a negative. So why do you think we have a negative answer here? Well, the reason is because we treat this reaction as a system, and after the reaction, heat is given off. Heat is leaving the system. So we have energy that's leaving the system. And if the system is losing heat, then we have to minus it. So anytime we see negative as an answer, we can instantly know that the system is giving off heat to the surroundings, and that's called an exothermic reaction. And if heat was being added to the system, this number would be positive, and it would be an endothermic reaction. Okay, so now we have our value here of negative 10,941.2 kilojoules of energy, and it's per 2 moles of C8H18, because remember, our reaction balanced, we involved 2 moles of it. So it's important to carry that over with any further calculations. We use this number for its identity is tied to this. So in other words, we could also write negative 1094.2 kilojoules of energy, divide that by 2, and we'd have that number per 1 mole of octane. Okay, so we can move on here to our next step, step number 3, Now we have to take 360 cubic centimeters and convert that to moles because of our previous calculation of the enthalpy of combustion is in moles. So if we want to know how much energy, we have to make that conversion first. And what we have known, and it's kind of handy here, is that 1 cubic centimeter is equal to 1 gram. So using that and the molecular weight, forgot a T there, the molecular weight of octane, we can go ahead and make that conversion. So the molecular weight of octane is 114.23 grams per mole, and there's that per mole again. So 1 mole of octane is going to weigh 114.23 grams. And real quick, it's really easy to calculate the molecular weight of any molecule using a periodic table and these numbers here. So I know that the molecular weight of carbon is, of a carbon atom, is about 12.01 grams per mole. And that of hydrogen is 1.008 grams per mole. So we do 12 times 8 plus 18 times 1.08, and that's how you get that number there. So using that number, we know that 114.23 grams of octane, because we have a 1-to-1 ratio, is going to be equal to 114.23 cubic centimeters of octane. And that makes it really easy to just make the final transition here of 360 cubic centimeters of octane. We're going to multiply that by this identity here, and all this is 1. This value right here is just 1, so we're completely allowed to do that. And all it does is transfer units, and it cancels things out. Since we have cubic centimeters on the bottom here, that's what's going to cancel. And after the calculation, we're left with 3.152 moles of octane in its liquid state. Alright, so now we're almost done here. We've done all the lengthy calculations, and the last step is just converting from moles to joules. And we can do that because we have our identity here from earlier. So we have 3.152 moles of octane, and we're going to multiply that by what we figured out earlier, and that is that negative 10.9412 megajoules, or 10,941 kilojoules of energy, is equal to 2 moles of octane. And that's in the formula of the combustion, the enthalpy of combustion of octane. And that's why we can do that and have that identity. And that turns out to be negative 17,243.33 kilojoules of energy, or 17.243 megajoules. Also in the request, Luke wanted to know if it could be done in horsepower, and we can convert that to horsepower using this right here. We have 735.5 joules per second equals 1 horsepower. So easy enough, we just use our identity, or multiplicative identity here, and we'll divide it by we'll multiply negative 17,243 kilojoules by 1 horsepower over 0.7355 kilojoules per second, and we have to change this to kilojoules so units match, and we're going to end up with this number here of 23.4 horsepower. Now the only problem with this conversion is it's supposed to be per second, but this is the energy given off by the entire reaction and without time as a factor. So this is how much energy, not necessarily horsepower per second, but just horsepower out of the total reaction possible. Now as for how much of that power is actually converted into what your car uses is a different story. Anyway, I hope this video cleared some things up for you viewers out, and stick around and I might have some more in the future. And again, special thanks to Luke Barber from Eagle Point for posing this fun chemistry problem.